Hello everyone, this is Rabah Delfouf. I am a doctor student from Department of Electronics Farhat Abbas University City in Algeria. First of all, thanks to the organizing committee of First National Online Conference in Materials Physics for giving me a chance to present my paper here. My paper title is Dielectric Study of Some Composite Materials at Microwave Frequencies. My co-authors are Professor Nasruddin Bouzid, Professor Nasruddin Rabah, and Professor Saleh Tlili. Now, I'm going to present my paper outlines. First, introduction. Second, experimental procedures, which contain three axes: samples preparation, machining of samples, and characterization bench. Third, results and discussions. Then conclusions, future works, and we end by some references. Now, introduction. The properties of attractive polymer titanium oxide composites with a high permittivity and low losses over a frequency range that can extend to tens of gigahertz have already opened a promising path for designers of microwave components. The focus here is on obtaining a high dielectric permittivity and low dielectric losses tangent coefficients over a broad dispersion spectrum. These two properties represent material selection criteria for better performance in certain specific applications such as microwave circuits. The composite materials that we used in this study are based on epoxy resin, which will be loaded with strontium titanate and iron oxide in order to determine their permittivities and conductivities for microwave electronics applications. Now we move to the experimental procedures. First, we talk about samples preparation. For the realization of the ternary composites, we use strontium titanate and iron oxide all in powder, bound by an epoxy resin in a liquid form. In this context, we have prepared several samples with different volume fractions. It should be noted that the proportion of the epoxy resin is fixed at 70% in all composites. Consequently, the proportion of the other inclusions, strontium titanate and iron oxide, vary between 0 and 30%. Now, machining of samples. For characterization on a TDR bench, tubular samples are needed. This shape is obtained by making an extraction with a hollow cylindrical drill of adequate dimension 7 mm in diameter from the parallel pipette samples. A hole of 3 mm in diameter is then drilled. Polishing is necessary to adjust the samples to the dimensions of the coaxial guide. The samples once prepared and machined looks like the one in this figure. Now we move to the characterization bench. The characterization technique adopted in our study is time domain reflectometry, TDR. It is a broadband microwave measurement method, simple and fast, designed around a system composed of a step generator, a coaxial line, a sampling oscilloscope, and a microcomputer. It is based on the study of the reflection generated by the interaction of an electromagnetic wave with the sample to be characterized, which is placed in a coaxial line. Now, results and discussions. We propose through this section the determination of the composite's properties. First, the figure 1 shows the static permittivity variation of composites at constant frequency value of 200 MHz overall load volume fractions. The examination of the graphic results elucidates a visible decrease in the real permittivity of the composites when the iron oxide volume fraction goes up. The Figure 2 shows the static conductivity profile as a function of the iron oxide volume fractions for a frequency value of 200 MHz, which is maintained constant. From the graphical examination of the results obtained, a visible decay of the static conductivity can be noted when the volume fractions of the iron oxide increases. And figure 3 shows the quality factor evolution of composites as a function of the iron oxide volume fractions. From the graphical results examination, we note that the values of the quality factor obtained vary between 18.5 and 23.5, which in fact explained the drop of the dielectric tangent losses varying from 0.05 to 0.04 for the composites. The values obtained are caliphate to the relatively large, which allows to have the maximum energy storage and the least dissipation possible. Finally, we conclude that ternary composites allowed us to analyze and clarify the effect of the nature of iron oxide on the dielectric properties of strontium titanate. The results of this study could be oriented towards applications in microelectronics, miniaturization of integrated circuit, or in microwave frequencies, antennas, and resonators. In future works, we'll cover the crystal structure effect study of charges on the dielectric permittivity, study the relaxation and the resonant phenomena, studying the quaternary composites, and verification of mixing laws for this type of composites. And here some major references. At the end, I want to thank everyone for listening to me and enjoy my presentation.